When you've got a plain text bit of information and you're trying to encrypt it and get it into that ciphertext, there are a number of different ways to go through the actual encryption process. And when we're talking about symmetric encryption, one of those methods is something called a block cipher. As the name implies, a block cipher is taking a fixed group of information and encrypting that fixed block all at one time. And usually these blocks are 64 bits long, they're 128 bits long, they're a size that is predetermined so that you're able to keep it the same when you're encrypting and decrypting. And in this block cipher, sometimes you'll have some text that doesn't quite fill up the block. So occasionally you will pad that data because you really do need a full block of 64 bits, 128 bits, whatever that size is, to be able to do that encryption. There are a couple of things we should keep in mind with working with some of these ciphers. One of these is something called confusion. That means that the resulting ciphertext that you get should look very different than your key. There should not be a way that you could look at the encrypted data and somehow figure out the key based on what you're seeing inside of the encrypted data. That is called confusion. And that means that it's a very complex and very complicated relationship between the key and the ciphertext that is created. Another concept is one called diffusion. That means that your output should be very, very different than your input. And if you were to change just one letter of your input, your output should be dramatically different. You shouldn't have minor changes to the output when you make minor changes to the input. That diffusion means that at least 50% of the output changes if you were to change one thing inside of your input. That way you can always be assured that the output that you get, that ciphertext is going to be as complex and difficult to figure out as possible. Another type of cipher is called a stream cipher, and just as the block cipher was only used with symmetric encryption, stream ciphers are only used with symmetric encryption. The encryption is done instead of entire blocks at a time. In a stream, it's done 1 bit or 1 byte at a time. It's all being done as the data is streaming by. And this is something that can run very, very quickly. It usually uses very low hardware complexity. You don't need a lot of fancy chipsets, a lot of calculations to make this happen. So it's something that can be done very, very, very quickly as the data is streaming by. And that makes sense. If you're streaming data by very quickly, you would need to use a method that's able to keep up with that stream. One important aspect to stream ciphers is that something called the initialization vector, the IV, should never be the same when you're starting to do some of these streams. Otherwise, somebody may be able to figure out that initialization vector that you're using and the cipher and the key that's being used and apply it every time you send data across the network. So one very important part of cryptography and the way that people use stream ciphers and be able to use initialization vectors in general is to make sure your IV is always changing whenever you're using it to encrypt information.
Hello friends, welcome to our channel. So in the earlier sessions we have seen the difference between a block cipher and a stream cipher. So in the stream cipher, we are just converting the plain text to the ciphertext bit by bit. And in the block cipher, we are just considering a group of characters and we are considering a block, and at a time each block will be processed so that the plain text of each block will be converted into the ciphertext. So that means a stream cipher is a bit by bit and the block cipher is a block by block. The conversion of plain text to ciphertext is performed in a block by block. So let us have a look on a block cipher design principles. So what are the design principles of a block cipher? So before going to this block cipher design principles, so most of the block cipher techniques will follow a common structure, that is a fizzle structure. So most of the block cipher techniques will follow this fizzle structure. We can call it as a fizzle or a fizzle, right? So fizzle structure. So what is a fizzle structure? So before going to the algorithms of a block cipher, we have to know this fizzle structure. So here in this fizzle structure, the first step is the plain text blocks is processed in two equal halves. So that means the first step is we have to divide the plain text in two halves, two equal halves. So plain text, and we have to divide it as two equal halves. This is the left half and this is the right half. And on the right half, we have to apply in a function. We have to apply the function. So a function may be anything, any logical function it may be, right? So depends upon the algorithm, the function will be varying. But the right half will be applied in the function. So this is the function. That function, what is the function? Means that depends upon the algorithm. So it may be a logical functions. So, and in function we will use a separate key. So key 1. And this output from this function will be XORed with the left half, and the output from this left half and this right half will be swapped. So that means the left half will be stored in rightmost bits, and similarly the right half will be saved in leftmost bits. So here again left and R. So the same process we call it as a round, a single round, and the process of converting this plain text to the ciphertext will be done in number of rounds. So the count, that means that the how many rounds we have to apply, that depends upon the algorithm we are using. So each algorithm will be having a different number of rounds. So, but if any plain text follows this structure, we call it as a fizzle structure. That means that particular algorithm follows the fizzle structure, fizzle structure. That means any plain text in any algorithm, if the plain text is divided into two halves and all the functions are applied on the right half, and the result of this function is XORed with the left half, and next swapping is there, and this process is continuously repeating in number of rounds, then we call that algorithm as a fizzle structure. That algorithm is having this fizzle structure. So here the security mainly depends on the functions, the number of rounds, and the number of keys. So here the key also, we will have a master key, and in each and every round we will use a separate subkey. That means from the master key we have to generate different subkeys. So depends upon the number of rounds, we have to then create a number of subkeys. So for example, if our algorithm is having a 10 rounds, that means a processing is done in 10 rounds, so we need to generate 10 subkeys from the master key. So this is again the left half, right half. Again the right half is applied to the function where the subkey 2 is used, and the result is XORed with right half. Again, this will be saved in right half and this will be saved in left half. So this we call it as a, see, this we call it as a round function, round function. So likewise it will be keep on going. So this is called a phasor structure. That means the first, the plain text in two equal halves. In two equal halves. Next, number of rounds. So the plain text is processed in number of rounds to get the ciphertext, and number of subkeys and swapping. So swapping of two halves, right to left and left to right. So if any algorithm follows these concepts, we simply say that that particular block cipher algorithm follows the phasor structure. So this is very important. And now if we look at the block cipher design principles, all these are the block cipher design principles. So first one, two halves. Next one, the number of rounds, number of subkeys, swapping, and the subkey size and the block size. All these are the block cipher design principles. Now let us see that. Alright. So this is all about the phasor structure. So in the next classes we are going to see the block cipher algorithm that is called a DES algorithm, data encryption standard algorithm, which follows the phasor structure. So that means in that algorithm also the plain text is processed in two equal halves, and the right half is applied to the function in which the subkey is used, and the result will be XORed with the left half, and finally the swapping is done. And this process will be repeated in number of rounds, and this number of rounds will be dependent on the algorithm. Now, so hope you understood this phasor structure. So if you see the example for this phasor structure, so that you can clearly understand. So in the next session I will say the example for this phasor structure, that is the DES algorithm, data encryption standard algorithm. So now let us have a look on block cipher design principles. Block cipher design principles. Block cipher design principles. So first one is block size. So this is the CE one, that is, as we are seeing this block cipher design principles, the plain text is processed in terms of blocks, so compulsorily there must be a block size. So here the block size is the size of the plain text. So whatever the plain text size is there, automatically we will get the same size of ciphertext. So if you process 10 bits of plain text, we will get the 10 bits of ciphertext. That means the length of the plain text and ciphertext are same. So the first one is block size, key size. So we have to use a key from which we have to generate the subkeys. So key size. Next, number of rounds. So the plain text is processed to the ciphertext in number of rounds. So in each round the same process will be going on. And subkeys. Subkeys count or number of subkeys. So in each round we have to use a separate subkey. That means from this key, master key, we have to generate the subkeys. That depends upon the algorithm. Next, round function. So in each and every round we will use the function, one function. That's it. It may be a logical function, right? So that depends upon the algorithm. So for every round we have to use the same function. And last but not the least, the plain text in two equal halves. The plain text is processed in two equal halves. So these are the design principles of any block cipher algorithm. So hope you understood these design principles. And here the security depends on the number of rounds, subkeys, and this round function. So if number of rounds increased, the complexity will be increased and also the security will be increased. The data will be more secure. And if the subkey count, if number of rounds are increased, automatically the number of subkeys will also increase. So automatically the security will also increase. Round function. So if the round function is more complex, the analysis of that algorithm will be very strong. So it is very difficult to the cryptanalyst to attack the data or to break the algorithm. So the security related issues are number of rounds, number of subkeys count, and the round function in the block cipher algorithm. So this is all about the phasal structure and the block cipher design principles. Hope you understood this simple concept. So let us stop here. In the next session we will go with the algorithm, very important algorithm, that is a DES algorithm, data encryption standard. So which is a block cipher symmetric algorithm. If you like my videos, share my videos with your friends and subscribe to my channel. And if you are having any doubts regarding network security, feel free to post your sessions in the post your doubts in the comment section, so that I will definitely try to clarify all your doubts. So thanks for watching and don't forget to subscribe to my channel. Thank you very much.
A widely used symmetric encryption scheme is based on the Data Encryption Standard, or DES. It was published in 1977 and standardized in 1979. In DES, the key is 64-bit, which is 8 bytes. But for each byte, there's one parity bit. Therefore, the actual value in the key is only 56-bit. And the output ciphertext is again a 64-bit block. Here's a high-level view of DES. There are 60 rounds of operations. From the original 56-bit key, 16 subkeys are generated, one for each round. The process of decryption with DES is essentially the same as the encryption process. It works as follows. Use the ciphertext as input to DES, but then for the subkeys, they're used in reverse order. That is, use K16 at the first round of decryption, use key 15 in the second round of decryption, and so on and so forth. That is, for decryption, we run the same algorithm, but only the keys in reverse order. Recall that diffusion is one of the principles in encryption, and it is typically achieved through permutation. In DES, permutation works by changing the positions of the bits. Recall that DES has 16 rounds of operations. Each DES round has the same operations and uses a different per round key. Each DES round takes as input the ciphertext produced by the previous round and outputs ciphertext for the next round. The input is divided into the left half and the right half. The output left half is just the right half of the input. The right half of the output is the result of XORing the left half of the input and the output of the Mangler function. The Mangler function takes as input the 32-bit input right half, expands it to 48-bit, then XORs it with the 48-bit program key, then use the S boxes to substitute the 48-bit value into a 32-bit value. We can also use algebra to represent the operations in a death round. That is, the left half of output is the right half of the input, and the right half of the output is the result of XORing the left half of input and the result of a Mangalore function, which takes as input the right half of the input and the program key.